Hello everyone. In today's lesson, we're going to be looking at algebraic methods for calculating limits. To begin with, we're going to be looking at the limit laws. So our first limit law says that if we have the limit as x approaches a for two functions, f of x plus or minus g of x, this will be equal to, so we have the limit as x approaches a for f of x plus or minus g of x, then this will be the same thing as the limit as x approaches a on f of x plus or minus the limit as x approaches some value a on g of x. Our second limit law says that if we have the limit as x approaches some value a and it is some constant times our function f of x, this is going to be equal to c times the limit as x approaches a on our function f of x. Our third limit law is that if we have the limit as x approaches a and we have some function f of x and then times some function g of x, this is the same thing as the limit as x approaches a function f of x times the limit as x approaches a on g of x. If we have the limit as x approaches a for our function f of x divided by the function g of x, this is equivalent to the limit as x approaches a on our function f of x divided by the limit as x approaches a on the function g of x. Now, this is specifically if the limit as x approaches a on g of x does not equal to 0, because in that case we would have our fraction would have a 0 in the denominator, so this implies that the limit as x approaches a on g of x cannot be equal to 0. Then we have the limit law. If we have the limit as x approaches a, if we have our function f of x and we take this entire thing to a power, let's say n, this will be equivalent to the limit as x approaches a on our function f of x, the entire thing, including the limit, to the power n. And this is for when n are positive integers. We also have the limit as x approaches some value a on a constant c will just be equal to that constant c. We have the limit as x approaches a on some variable x. This will be equal to that constant a. If we have the limit as x approaches a, x to the n, this is equal to a to the n. Because what's happening here is that if you have x to the n, this is the same thing as taking the limit as x approaches a on x, taking the whole thing to the nth power. We said limit as x approaches a on x is equal to a, so this should just be a to that power. We have the limit as x approaches a, nth root of x, and this is equally going to be, just like before, it's going to be the nth root of whatever that value a is, where n has to be a positive integer. Just like before, if we have the limit as x approaches a on some function f of x, and we're taking the nth root, this is the same thing as taking the nth root of our limit as x approaches a on our function f of x. And this is because, again, our nth root is the same thing as just saying a function of x to some power, just like we did here. The only difference, though, is instead of being to the nth power, where n is a positive integer, now we would have that n is some fraction integer. So it'd be like saying limit of x approaches a, f of x to the 1 over n power, in which case we could take the 1 over n power of the entire thing, so it ends up being the equivalent rule. Our next definition is that if we have the limit as x approaches a on some function f of x is equal to L, which, if you remember, this is our definition of a limit. This is true if and only if the limit as x approaches a from the left side on f of x is equal to L, and the limit as x approaches a from the right side is equal to L. And this is because we are going to have to consider left side limits and right side limits. So the limit itself, this statement is only true if both approaching from the left and the right are converging on this same value L. So if f of x is a continuous function, then the limit as x approaches a, f of x equals f of a. So that is to say, if we have a continuous function, then the limit as x approaches a, f of x will be equal to our function at a. And this is called our direct substitution property. So what this means is this definition here is true if it's approaching some value L, even if it cannot be that value. So this might be something like if you have some function, you have a whole, let's say, and then something like this. Or if you have something like this, and instead maybe for some reason it jumps here, or something like that. In which case, both of these would be true because from the left and from the right, we are approaching the same limit. This is saying that if we have some continuous function, meaning there's no hole, that is, as I'm approaching from the left and as I'm approaching from the right with f of x, this would be the same thing as the specific point, the function at a. This is called our direct substitution property. So now that we have all these rules, let's do some examples to see how they hold up based on different scenarios. So let's say that given we have the limit as x approaches 3, so this is our a in this case, on our function f of x is equal to 1, we've got the limit as x approaches 3 for g of x is equal to -2, and our limit as x approaches 3 for h of x is equal to 0. So we have 3 different functions, and we're looking at what happens with each of them as we approach, using the limit, as we approach 3. So the first question then is, what would the limit as x approaches 3 on f of x plus 3g of x be? So what I'm going to do is I'm going to break this down by focusing on doing every single one of our limit rules as we do this. So the first thing I'm going to look at is the fact that when I have the limit of some function f of x plus or minus some function g of x, I can actually rewrite this as the limit of the first function plus or minus the limit of the second function. So this is going to be equal to the limit as x approaches 3, f of x, plus the limit as x approaches 3 times g of x. Now what we're going to do is we are going to use our property where if we have the limit of some constant times a function, this is the same thing as the constant times the limit of the function. So this then becomes the limit as x approaches 3, f of x, plus 3 times the limit as x approaches 3, g of x. And now with this, we can actually solve for this because we know that the limit as x approaches 3 on f of x is equal to 1. And then so plus 3 times the limit as x approaches 3 for g of x is equal to -2. So we are left with 1 plus 3 times -2. 3 times -2 is equal to -6. So 1 minus 6 would give us -5. So next what we're going to do is we're going to look at what if I have the limit as x approaches 3 for g of x cubed. So this is going to be using the property where this is the same thing as saying the limit as x approaches 3 on g of x all cubed. So we said the limit as x approaches 3 g of x is equal to -2. So this is equal to -2 cubed, which is equal to -2 times -2 is +4. +4 times -2 gives us -8. And then for our third example, we have the limit as x approaches 3 square root of f of x. And again, this rule was that if we had the square root of f of x and we're taking the limit of that, that's the same thing as saying we're taking the limit as x approaches 3 on our function f of x, and we will take the square root of the entire thing. Well, the limit as x approaches 3 f of x we said was equal to 1, so this is equal to the square root of 1, which is equal to 1. And looking here at the slides, you can actually see that this agrees with exactly what we did in these 3 problems. Next, we're going to be looking at the limit as x approaches 3 2f of x divided by g of x. The limit as x approaches 3, g of x over h of x. And the limit as x approaches 3, g of x times hx divided by fx. So we'll start with the first one, where we have the limit as x approaches 3, 2 times f of x divided by g of x. Now, as before, this would be equal to the limit of the numerator divided by the limit of the denominator. So we have the limit as x approaches 3, 2 times f of x, divided by the limit as x approaches 3, g of x. Now, this limit as x approaches 3, g of x, we're good to go on that one. But here we have some constant, right? This is not the same thing we have written here. We have limit as x approaches 3, f of x. We don't have limit as x approaches 3, 2f of x. So what we're going to do is we're going to use our property where we can pull this constant out. This is going to be equal to 2 times the limit as x approaches 3, f of x divided by the limit as x approaches 3, g of x. So in this case, this is going to be equal to 2 times the limit as x approaches 3, f of x is equal to 1. And the limit as x approaches 3, g of x is equal to negative 2. This gives us 2 over negative 2, which is equal to negative 1. For the next one, we have the limit as x approaches 3, g of x divided by h of x. So in this case, when we have the limit of a fraction, this is just going to be the limit as x approaches 3, g of x, divided by the limit as x approaches 3, h of x. Now in this case, we actually have both of these terms here. So the limit as x approaches 3 for g of x is just going to be equal to negative 2. The limit as x approaches 3, hx is going to be equal to 0. So in this case, we can't do this operation because we have the limit as x approaches 3, hx equals to 0, which gives us a 0 in the denominator, which means that this one does not exist. So what we might have to do in this case is if we wanted to try this, if we knew anything else about this function at hx, we could possibly look at what is happening as we approach 3 from the left side, what is happening as we approach 3 from the right side, and then from there we might be able to get its limit. So for the last one, we have the limit as x approaches 3, we have gx, hx divided by f of x. So this is going to be equal to the limit as x approaches 3 of my numerator. So this will be gx times hx divided by the limit as x approaches 3, f of x. Now this top one, I can't take the limit as x approaches 3, gx times hx. So what I'm going to do is I'm going to use my property where the limit of one function times another function is the same thing as the limit of the first function times the limit of the second function. So this is going to be equal to the limit as x approaches 3, gx times the limit as x approaches 3, hx divided by the limit as x approaches 3, f of x. Now this I can solve because the limit for g of x is equal to negative 2 times the limit of hx is equal to 0, and then the limit of f of x is equal to 1. So this would give me negative 2 times 0 is 0 divided by 1, which is equal to 0. So in looking at the slides, you can see that this matches exactly what we got when we were working this out together. For our next example, we want to evaluate the limit as x approaches 5 for 2x squared minus 3x plus 4. Now we're going to be using the property where we have the limit of some function plus or minus some other function, but in this case we have 3 functions. Well, this still works. It follows the same trend, so this is going to end up being the limit as x approaches 5, 2x squared minus the limit as x approaches 5, 3x plus the limit as x approaches 5, 4. Now again, we can solve some of these, but not all of them. And again, I don't want to skip any steps because I don't want anyone to wonder how we got to any particular point. So what I'm going to do now is this one, we have a constant times x squared. So I'm going to pull that constant out first. So this is going to end up being the limit as x approaches 5 I'm going to pull that 2 out, so this will be 2 times that limit, x squared. Minus, again, I have a constant, so I'm going to pull that constant out, 3 times the limit as x approaches 5, x, and then plus, I can actually just evaluate this one now, and I'm going to do it to save myself from writing. The limit as x approaches 5 on some constant is just going to be the constant. So this is going to be plus 4. Now, this one, we're actually good to go. 3 times the limit as x approaches 5 on x. This one, though, we have x squared. So what we're going to do is we're going to use the property where if we have the limit of x to some power, it's the same thing as whatever the limit of x would be to that power. So this is going to be equal to 2 times the limit as x approaches 5 on x, and then I'm going to square whatever this would be. And then minus, I'm going to leave this the same for now, limit as x approaches 5 plus 4. And now that we have it in this form, we can actually solve for this by doing our direct substitution method. Can I plug in the limit as x approaches 5 on the function x? Well, yes, we just said that the limit as x approaches some a, x would be equal to that value a. So this is going to be equal to 2 times 5 squared minus 3 times the limit as x approaches 5 to x is going to be 5, so this is going to be minus 3 times 5, and then plus 4. So 5 squared is going to be 25. 25 times 2 is going to be equal to 50, minus 3 times 5 is going to be 15, plus 4. So negative 15 plus 4 is the same thing as saying negative 11. 50 minus negative 11 is going to give us 39. And then looking here at the slides, you can see that this agrees with exactly what we did. For our next example, what we want to do is we want to evaluate the limit as x approaches negative 2, and we're going to have our numerator of our fraction is going to be x cubed plus 2x squared minus 1 divided by 5 minus 3x. First thing we're going to do, I'm going to take this as the limit of the numerator divided by the limit of the denominator. So this is going to be the limit as x approaches negative 2, x cubed plus 2x squared minus 1 divided by the limit as x approaches negative 2, 5 minus 3x. Then I'm going to take that limit and I'm going to apply it to every single function within our numerator and denominator. So this is going to be the limit as x approaches negative 2, x cubed, plus the limit as x approaches negative 2, 2x squared, minus the limit as x approaches negative 2, negative 1, divided by the limit as x approaches negative 2, 5, minus the limit as x approaches negative 2, 3x. So now we have a lot to do on this one. So in this case, I'm going to talk through every step, but I might skip a few steps just to make it a little bit faster. So this first one, we have the limit as x approaches negative 2, x cubed. We can take this as the limit as x approaches negative 2 on x, and we can cube the entire thing. For this next one, we have a constant that we can pull out. So I'm going to do that first. So this is going to be plus 2. And then I have the limit as x approaches negative 2, x squared. So this is the same thing as if I took the limit as x approaches negative 2, x, and then I'm going to square the entire thing. And as for this next one, it's minus the limit of a constant, which means it's just going to be that constant. So plus 1. Divided by, now this one, again, we have the limit of a constant. So this is just going to be equal to that constant. So this could be 5. Minus, this one has a constant in front of our x. So we're going to pull that constant out. So we're going to get minus 3 limit as x approaches negative 2, x. So now that all of our limits are in terms of x, we can actually evaluate this. So doing this, we're going to have the limit as x approaches negative 2, x is going to be negative 2. So negative 2 cubed is going to be negative 2 times negative 2 is positive 4. Positive 4 times negative 2 is going to be negative 8. The next thing we have is plus 2 times, we have limit as x approaches -2. This is going to give us -2. Squared is going to give us +4. And this is going to be +1. In our denominator, this constant is still 5. Minus 3 times the limit as x approaches -2 on x is going to be -2. So this gives us -8 plus 2 times 4, which is equal to 8. So -8 plus 8 is going to be 0. Plus 1 will leave us with 1 in the numerator. 5 minus 3 times -2. So 3 times -2 is -6. So 5 minus -6, same thing as saying 5 plus 6, which is going to give us 11. So this would give us 1/11. For our next example, we're looking at what is the limit as x approaches 1, x squared minus 1 over x minus 1. First thing I'm going to do is I'm going to first break this down just like we did before, and I'm going to be a little bit quicker on some of these just because now that we've kind of been talking through the rules, we're going to look at can we do it without necessarily showing every single step. So this might be the limit as x approaches 1 on x squared minus 1, and this will be over the limit as x approaches 1, x minus 1. Now, if we were to split this, we're going to end up with the limit as x approaches 1, x squared, so this is going to be the limit on x, the whole thing is going to be squared, minus the limit as x approaches 1, -1, divided by the limit as x approaches 1, x minus the limit as x approaches 1 plus 1, because I pulled the negative out. So now if we were to evaluate this, if I were to plug in 1 here, I would get 1 squared. So this is going to be equal to 1 minus, I also did the same mistake earlier, this should be plus 1 because I pulled that minus out. So in this case would be -1 divided by the limit as x approaches 1 on x is going to be 1, and then again -1. This is going to give me 0/0, which means that this does not exist. Now, this is actually what's called an indeterminate form, which we actually will look at a method we can use to solve this later on in the course. But one thing that we can do currently is we could try to see, is there anything we could do to do some cancellation? So let's look at this x squared minus 1 here. So if we were to break this down into x squared minus 1, what could we multiply to give us -1 and then adds up together to cancel out to give 0? And this would be equal to x minus 1, x plus 1. Now, if we did this, right, if we FOILed this out, first would give us x squared minus x, outer would be plus x, and then inner, or last would be -1. So the plus x and minus x would cancel. This would leave us with x squared minus 1. So now rewriting this using that, we could have the limit as x approaches 1, x minus 1, x plus 1, divided by x minus 1. Now, if we look at this, you might notice that we have x minus 1 on the top and the bottom, meaning that we can actually cancel these out. And now what we're looking at is the limit as x approaches 1, x plus 1, which then using our limit rules would be the limit as x approaches 1, x plus the limit as x approaches 1, 1, and this would be equal to 1 plus 1, or 2. And then looking at our slides here, you can see that this matches exactly what we did. Now again, I did break down the steps a little bit more, but you can still see that it follows exactly what's on the slides. Now what we're going to do is we're going to look at what if we were to take the limit of a piecewise function. So we're going to look at if we have limit as x approaches 1, g of x, where this is going to be equal to x plus 1 if x is not equal to 1, and this is going to be equal to pi if x is equal to 1. So now what we have to do is we actually have to consider as the limit as x approaches 1 is going to be which of these? Well, remember, when we're approaching 1, this means that we're not at 1, meaning we're going to be focusing on this when x is not equal to 1. So this means that we would have the limit as x approaches 1, x plus 1, which is just going to be the limit as x approaches 1, x plus the limit as x approaches 1 on 1. This is going to be equal to 1 plus 1 equals 2. Now, if f of x equals g of x when x is not equal to a, then the limit as x approaches a, f of x, is equal to the limit as x approaches a, g of x. So pretty much what's happening in this case is that we have some function, x plus 1, right? So it's going like this. And then suddenly at 1, where if we were to try to plug this in, we'd get 2, but it actually jumps up to pi, which means it would be above. It looks something like this. Now, one thing I want to point out is if we have some function f of x that is equal to g of x when x is not equal to a, then if we take that limit as x approaches a on that function f of x, this is going to be equal to the limit as x approaches a on that g of x. This means that if our functions are equal when they do not have x equal to a, then our limit is going to be whatever the limit on that function would be as x approaches a. Next, we're going to look at what is the limit as h approaches 0 for 3 plus h squared minus 9 divided by h. So if we were to first look at our substitution method, let's say we substitute 0 in for everywhere we have h. This would be 3 plus 0, which is 3, squared would give us 9. So 9 minus 9 is equal to 0. Divided by 0, this would give us 0 over 0, which again is indeterminate. So this leads us to, if we're going to be able to solve this, not using the method we'll look at later on called L'Hopital's rule, then we need to probably look to see if there's some sort of cancellation we can do. So because we have 3 plus h squared, what I'm going to do is I'm actually going to expand that out, and this is going to be the limit as h approaches 0, and then I'm going to do my first term. So first is going to be 3 times 3, outer, which is going to be 3 times h, so this is going to be plus 3h, inner, which again is going to be plus 3h, and then last is going to be plus h squared. And then I still have that minus 9 divided by h. Now, just a reminder, when I said that I'm expanding this out, I'm basically doing this. It's 3 plus h times 3 plus h, and then I'm multiplying the first terms, the outer terms, the inner terms, and then the last terms. And that's where this came from. So I had this turn into this here, and then I brought the minus 9 down. So now we're going to see, is there anything we can do for some cancellation? So I can actually rewrite this as, first of all, negative 9 and positive 9 are going to cancel. And you'll notice we have 3h plus 3h plus h squared. So this is going to be the same thing as saying 6h plus h squared divided by h. And then we're taking the limit on that as h approaches 0. Now, if we were to try to substitute now, we'd still get 0 over 0, right? Because we get 0 plus 0 divided by 0. So that still doesn't work. So now what I'm going to do is I'm going to look at, is there any cancellation I can do? And I can, because every one of these terms has an h in it. So this would be the same thing as taking the limit as h approaches 0. I'm going to pull an h out of the numerator. So this is going to be 6 plus h divided by h. These h's will cancel, and this will just leave me with the limit as h approaches 0, 6 plus h. Now I can do my substitution, plug in 0 for h, and I'm left with 6. What about if I wanted to take the limit as x approaches 0 for the absolute value of x? And we're going to say this is equal to 0. So what we have to do is we actually have to consider that when we take the absolute value, this is a piecewise function, because if you remember, the graph of an absolute value looks like this. Any value that is greater than 0 will just be that value. Any value that is less than 0 will be the positive equivalent of that value. So this means that what we're doing is when we take the limit as x approaches 0 on the absolute value of x, this is going to be equal to the limit as x approaches 0, where it's going to be x if our x is greater than or equal to 0, and it's going to be negative x if our x is less than 0. So what we're going to do is we're actually going to look at the limit from both sides to prove that this is true. Because remember, our idea is that if we have the limit from the left is equal to the limit from the right, and they're both equal to that 0, this statement would be true. So let's start by looking from the left. So we have the limit as x approaches 0. Now, because we're coming from the left, I'm going to put a little minus sign here. Now, because we're coming from the left of 0, that means we have a negative number, meaning we're going to be using this function here, negative x. So this is pretty simple to solve. You could think of this as negative 1 times x. You could pull that negative 1 out, and this is going to be the same thing as saying the negative limit of x as x approaches 0. Now, as x approaches 0, the limit of x is going to be 0. Negative 0 is just going to be equal to 0. Now, what about if we approach from the right side? So now we're going to have the limit as x approaches 0 from the right side. Now, if we're approaching from the right, that means we have a positive value, which means that it's just going to be the function x. So the limit as x approaches 0 for x is just going to be 0. So the fact that these two are equivalent, this does mean that this statement is true, that the limit as x approaches 0 for the absolute value of x is equal to 0. So we've actually shown that this is true by looking at the limit from the left side and the limit from the right side, breaking this into a piecewise function of what's happening on the left of 0 and what's happening to the right of 0. Next, what we want to do is we want to prove that the limit as x approaches 0, absolute value of x over x does not exist. So for this problem, again, we are going to be using the fact that if we have the absolute value of x, this is going to be equal to x if x is greater than or equal to 0, and negative x if x is less than 0. So we're actually going to be looking at it from two different sides. We're going to look at it as we approach from the left, and look at it as we approach from the right. So for the left, we're going to have the limit as x approaches 0 from the left, and this absolute value of x, if we're approaching from the left, is going to be equal to negative x over x. So before we actually take the limit, we have negative x over x, which if we cancel those out, we're just going to be left with the limit as x approaches 0 from the left on negative 1, which is going to be equal to negative 1. Now we're going to look at what happens if we approach as x approaches 0 from the right. Well, if we're approaching the right, this means we're coming from the positive side. This means that we are going to have our function as x over x, which of course this will just be equal to 1. The limit of 1 is going to be equal to 1. Now, because this limit as x approaches 0 from the left on our absolute value of x over x does not equal to the limit as x approaches 0 from the right, absolute value of x over x. Because these are not equal to each other, this means that the limit does not exist. And you can see that exactly here in the slide. Because negative 1 does not equal 1, therefore our limit does not exist. For our next example, we want to find the limit as x approaches negative 9, 2x plus 18 divided by the absolute value of x plus 9 if it exists. So the first thing I might look at is if I were to plug in negative 9, what's going to happen? Well, I get 2 times negative 9 is negative 18. Negative 18 plus 18 is 0. And then if I plug negative 9 in here, I get negative 9 plus 9 is 0. Absolute value of 0 is 0. I have it dividing by 0, so that's not going to work. So what we're going to have to do is, again, we're going to have to look at breaking this into a piecewise function. So if you remember, what happens with our function by having that plus 9 in it is it's taking every value we have and it's shifting it to the left by 9. So instead of having our absolute value where it's around the origin, it's actually going to be the same thing, but around the point negative 9. So this means that, in this case, the absolute value of x minus 9 is going to be equal to x plus 9 when x is greater than or equal to negative 9, and it's going to be equal to minus x plus 9 when our x is less than negative 9. So all we've done is we've shifted by 9. So meaning if I were to plug in a negative 9 here, I would get negative 9 plus 9 would be 0. If I plug in any value that is greater than negative 9, for example, negative 8, I would get some positive value. If I were to plug in negative 9 into this, I would get negative 9 plus 9 is 0. Take the negative of that, this would be negative 0. But if I get any value that's less than negative 9, let's say negative 10, I would have negative 10 plus 9 would be negative 1. take the negative of that, get positive 1. So it's same idea, except for we've shifted over by 9 to the left. So what I'm going to do is I'm first going to break this down, again, into two limits. Limit as x approaches -9 from the left, and the limit as x approaches -9 from the right. So this is going to be, when I'm approaching from the left, this is 2x plus 18 divided by, now remember, from the left, this is going to be minus x plus 9. When I'm approaching from the right, this is going to be 2x plus 18, x plus 9. Now with this, we're able to solve both of these limits. So what do? Well, first things first, if I were to distribute this negative, if I were to plug in my -9, what's going to happen? So in this case, what I'm going to do is I'm going to pull a 2 out of this numerator. So I'm going to have the limit as x approaches -9 from the left, pull a 2 out, and I get x plus 9 divided by minus x plus 9. These x plus 9s will cancel, and I'll be left with 2 over -1, which is equal to 2. I'm going to do the same thing over here, and this is going to leave me with, so I'm just going to say this is 2 x plus 9. This x plus 9 is going to cancel this x plus 9. So this is going to leave me with the limit as x approaches -9 from the right is going to be 2 over 1, which is going to be equal to 2. So then comparing my limits, as I approach -9 from the left, I came to -2. As I approach -9 from the right, I got 2, which means that the limit does not exist. This statement is not true because it's not approaching the same value. Next, I want to introduce what's called Squeeze Theorem. So this says that if we have f of x, which is less than or equal to g of x, which is less than or equal to h of x, where x is very near a, and the limit as x approaches a on f of x is equal to the limit as x approaches a on h of x is equal to L, then that means that the limit as x approaches a for g of x has to also be L. So what this pretty much means is this. If I have, let's say, some function f of x, which is here. Let's say it approaches some value as x approaches a. We'll just say that a is right here. And if I have h of x, which is equal below here, and also approaching this a value. If I have some g of x, which is always between these two values, then as f of x approaches a and h of x approaches a, then this means that whatever g of x is, it will also have to approach that a as I take the limit L as x approaches a. Suppose that we have 3x minus 2 is less than or equal to our function f of x, which is less than or equal to x squared minus 3x plus 7. And we want to find the limit as x approaches 3 on f of x. So what we're actually going to be doing is we're going to be looking at the limit of our left side of our whatever function this is, and the limit of our right side function, and we're going to see, do they actually converge on something? Because we said that our function f of x is always between these two values. It's always greater than or equal to our first function, always less than or equal to our second function. So then if we were to take the limit as x approaches 3 on 3x minus 2, if I were to plug 3 into this using my direct substitution, this is going to be 3 times 3 is 9, minus 2 is going to be 7. And if I were to take my limit as x approaches 3 on this function, which is going to be x squared minus 3x plus 7, this means that if I were to plug this in, 3 squared is 9, 9 minus 3 times 3 is 9, so 9 minus 9 is 0, plus 7 is going to be equal to 7. So this means that the function that is below f of x, or equal to, converges to 7 as x approaches 3. The function that is greater than or equal to f of x also converges to 7 as we take the limit as x approaches 3. This means that because these two are equal and f of x has to be between these two functions, this means that the limit as x approaches 3, f of x is equal to 7. And looking at the slide, this is a lot of times the way we'll actually write it, is that we'll have our two functions, we'll take the limit of those two functions while leaving it in terms of the inequality, and then we'll solve for each of those, and if it's between these two values, that shows you where your limit as x approaches 3 for f of x has to be. Now, one thing I want to point out is that with our squeeze theorem, the idea is that if you have two functions that are one above, one below, as they come together, that means that it's going to squeeze that middle function, because this has to be true, into the same limit. Now, if for whatever reason you had some limits that were not equal to each other, but this one was greater, the larger function was greater than the smaller function, this would give you a range of values. So let's say that instead you had 3 is less than or equal, the limit as you take this is 3, limit as you take this is 4. That would mean that you know that the limit as x approaches 3 f of x would have to be something between 3 and 4. We don't know the exact limit, but we would at least have a range of possible limits. So now let's do another example where we have the limit as x approaches 0, x squared sine 1 over x. And we're going to check if this is equal to 0. We're going to show that this is true. So first thing I'm going to do is I'm going to consider that if I plugged in 0 in the denominator here, we know that this is just going to be undefined, therefore we can't just do our direct substitution. So what we're going to do is we're going to consider the fact that if I have some sine function, that I know that this has to be between -1 and +1, right? And because I have some value that is close to 0, meaning that it's less than 1 or greater than -1, and I'm squaring that, that means that this value is actually going to be making it smaller. So if I can show that -1 is less than or equal to sine 1 over x less than or equal to 1, if I can show that the limit as these two approaches 0, then I should be able to show that this is true. So looking at this, we have this statement is true because the sign of anything will be between -1 and 1. So this means that we have a limit on what our possible functions can be. Now, because we have x squared times this, what we're actually going to look at is we're going to say that, okay, well, if I multiply every one of these by x squared, this would be -x squared is less than or equal to x squared sine 1 over x is less than or equal to x squared. So now all I have to do is I have to see, is the limit as -x squared and limit of x squared, as they approach 0, do they approach the same value? And if so, then that means that this would have to be squeezed into that same limit. So what I'm going to do is I'm going to take the limit as x approaches 0 on -x squared less than or equal to the limit as x approaches 0, x squared sine 1 over x less than or equal to the limit as x approaches 0, x squared. Now, if I take the limit of -x squared to as x goes to 0, right, I could pull that negative out, same thing as multiplying by -1. So this would be negative, the limit as x approaches 0, x squared. 0 squared is 0. 0, so -0, still 0, so we have 0 for our leftmost term. So we have limit as x approaches 0, x squared sine 1 over x less than or equal to. Same thing, if I take x squared and I take the limit as x approaches 0, 0 squared would be equal to 0. So therefore, we've shown that this, which is less than our x squared sine 1 over x, is approaching 0 as x approaches 0. And this x squared, which is greater than or equal to our x squared sine 1 over x, is also approaching 0 as x approaches 0. This means that it's squeezed in, meaning that as our limit as x approaches 0, x squared sine 1 over x also has to be equal to 0. And you can see that here on the slide, following exactly what we did. So now let's look at the limits of a couple of our trig functions. If we have the limit as theta approaches some value a, cosine of theta, this is going to be equal to cosine of that value a. If we have the limit as theta approaches a, sine of theta, this is going to be equal to sine of a. And then also if we have the limit as theta approaches a, sine of theta divided by theta, this is going to be equal to 1. So let's do some quick examples. Let's say that we have the limit as x approaches a, and we have sine 7x divided by 4x. Now, this doesn't really fit any of these, right? Because if we were to plug in a, we would have sine of 7a over 4a, which really doesn't help us. So what we're going to do to try to get rid of this sine of x is we're going to look at what's inside of it, and we're going to multiply by 7 over 7. So if we were to do that, multiply by 7 over 7, we now have the limit as x approaches a, 7 sine of 7x over 4x times 7. Well, because multiplication is commutative and associative, I can rewrite this as 4 times 7x. Now, the reason we can do this, remember, 7 over 7 is the same thing as 1, and we're just multiplying by 1. We haven't actually changed anything. So sine of 7x divided by 7x is equal to 1. So now we have the limit as x approaches a, 7 over 4, which will give us 7 over 4. Which, looking at the slide, you can see that follows exactly what we just did. For the next example, we're going to be looking at the limit as theta approaches 0, cosine theta minus 1 divided by theta. Now, this one is a little bit more complicated because we can't really use any of these rules right now, because if we were to just try to plug in 0, we would have cosine of theta would be cosine of 0, which would be 1. 1 minus 1 would give us 0 divided by 0. We'd have an indeterminate, undefined solution. So what we need to do is we need to think about, is there anything we can do and multiply the top and the bottom by that would allow us to get it into one of these forms? So in that case, what we're going to do is we're going to multiply by the reciprocal like we did earlier in this class. So this is going to be times cosine of theta plus 1 divided by cosine of theta plus 1. Now, as before, cosine of theta plus 1 over cosine of theta plus 1, same thing as multiplying by 1, so this doesn't change anything. So now what happens when we do this is this is going to be equal to the limit as theta approaches 0, and then what I'm going to do is I'm going to distribute this, so this is going to be cosine of theta times cosine of theta, which is going to be cosine squared theta, and then I'm going to do my outer terms. So my outer terms would be cosine of theta times 1. My inner terms would be minus 1 times cosine of theta, so those two would cancel. And then my last terms, negative 1 times 1 would be minus 1. Over, and this would be cosine of theta times theta plus 1 times theta. So I'm just going to leave this the same. Theta divided by cosine of theta. Now what do we do? Well, in this case, we're going to use the fact that if we have sine square theta plus cosine square theta, this is going to be equal to 1. And what I'm going to do is I'm going to move this cosine over here. So, I'm going to move this sine over here. So we're going to have that cosine of theta. So cosine squared of theta is going to be 1 minus sine square theta. So using this fact, this is going to be equal to the limit as theta approaches 0. It's going to be negative sine squared of theta divided by theta times cosine of theta plus 1. So for the next step, what I'm going to do is I'm actually going to split one of these sine thetas over this theta, right? Because if I have the limit of some fraction where I have two values in the denominator, it's the same thing as splitting it up. So it's because multiplication. So this is going to be the limit as theta approaches 0. And I'm going to pull out sine of theta divided by, I'm going to have that theta here, times. And I'm going to have my other sine theta. This one's going to be negative sine theta divided by this cosine theta plus 1. Now, if we look at this, right, remember this limit is for the whole thing. What I can do is this sine of theta over theta, when I evaluate this, the limit as theta approaches a, sine over theta is going to be equal to 1. So this term is just going to go to 1. This is going to leave me with negative sine theta, which I can pull that negative out. So this is going to be negative limit as theta approaches 0, sine theta divided by cosine of theta plus 1. And then if I take the limit of sine theta as theta goes to 0, sine of 0, I'm going to use my substitution method, is equal to 0. Let's do the substitution method for the bottom. Cosine of 0 is going to be equal to 1 plus 1 is going to give me 0 over 2, which is equal to 0. And then if you look at the solution I have on the slide, you will see that this follows exactly what we did here. So you can see that there's a lot of things here with our limit rules, and it's very important to have a really strong grasp of these rules because you can take much more complicated problems or things that look like you might not be able to solve them and then actually break it down and break it into individual pieces that are solvable that then allow you to have a solution. Now, I mentioned later on we will learn a trick that allows us to solve these undefined answers solutions much faster. But notice that this didn't stop us from being able to analytically solve these limits. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.